Thank you very much. So today we will continue. All right, so somehow today the lecture will be independent of what we did yesterday, but let me recall that yesterday we started from some basic things. So first of all, I introduced maximal operator, and more or less we can think that pointwise convergence of some sequences is equivalent up to a few things to the boundedness of the maximal operator or the tweak type. One of the maximal operator. Also, we introduced some ergodic setup. So we introduced ergodic averages, and we proved that in the case of linear trajectory, we have pointwise convergence. This was very called pointwise theorem. Right, and also we discussed a bit the case of Bourgain's ergodic theorem, where linear function n in the definition of ergodic averages is replaced by a polynomial. And we said that in this case, it's very hard. So far, no one gave a reasonable class, dense class for which we know convergence. Okay, so that's why we cannot apply in this case two-step procedure because we do not know dense. And that's why we need some more sophisticated tools which directly will give us pointwise convergence. So the first thing I want to introduce is the variational seminorm. So what happens here is we assume that we have some sequence AT. I is a subset of R. You may think that this is just a set of integers or dyadic numbers, or this is half space, or this is whole R. And then for such a sequence, we define the variational seminorm, which is LR norm of all possible differences. Okay, so for R equal to 1, it's quite easy to, if you have a given sequence, it's quite easy to compute this R variational. In the sense that what is optimal is to give as many points as possible, but if R is strictly larger than 1, then sometimes it's better to skip some points. So it's more tricky to compute it if you have a given sequence. What is important here is that if we know that the variational seminorm is finite, then immediately we know that AT is a Cauchy sequence. Okay, and this can be easily seen because if it is not a Cauchy sequence, it means that we have epsilon and we have infinitely many TJs such that the difference is greater than epsilon. So this can be estimated from below by epsilon times the R root of J. So when we tend with J to infinity, then we get a contradiction with the finities of R variational seminorm. Okay, moreover, we may think that the variational seminorm dominates maximal operator. Because if we put this AT0 on the left-hand side, then it's sufficient to observe that the difference between 2 points is dominated by the variational seminorm. This is clear from the definition because we have such differences, right? So it's just one difference. And on the other hand, okay, what is important here is that this is semi-norm in the sense that it's possible that this object is 0, even though AT is non-zero, right? But this situation can happen only if the sequence is constant. Okay, so to avoid this problem, sometimes if we want, we can redefine variational semi-norm and add supremum, right? But on the other hand, we know that supremum essentially is dominated by. All right, and in that way, we obtain a norm the functions on I. All right, so this is just the definition which we had on the previous slide. And here we have more properties. So the first one is that if we look at R variations as a function of R, then this function is non-increasing. And this follows from the nested property of small LR functions. So in practice, if we will look at R variational estimates for some operators, it means that if R is smaller and smaller, then it's harder to prove R variational estimate. And in the operators we will be discussing, so mainly averaging operators, and well, in particular, ergodic averaging operator. The critical point is R equal to 2. So it will turn out that we do not have two variational estimate, but we will have R variational estimates for all R greater than 20. The other thing, which is also very simple, is that if we have larger set I, then the R variation is larger, because well, we take the supreme over larger set, right? So there is nothing hidden there. Also, we can split R variational semi-norm if we have the following decomposition. But here, the important thing is that I1 and I2 are ordered, in the sense that I1 is smaller than I2. That is, maximal element of I1 is equal to the minimal element of I2. So here, the canonical example that we have, let's say, original interval AB and point C in between. So then the variation over AB can be split into variation over AC and CB. Okay, so this is the way this usually used. Also, if I is countable, then using triangle inequality for LR small norm, you can show this estimate, because we can treat separately this part and that part, so we do not assume that there are cancellations. Okay, and in fact, it works also for I which are uncountable, but then usually it does not make sense, because usually then the right-hand side is infinite, right? Unless we have that zeros. Okay, so usually we will use this estimate if we will be dealing with dynamic scales. So if I will be that itself, then there is a moment that this estimate will be good and will give us some sort of estimate for the operators. All right, do you have any questions? All right, so we are moving to, I think, a bit more complicated objects. So oscillation semi-norm. So here to introduce these objects, we first need to introduce this SJI set, which consists of sequences of length j plus 1. So in fact, we have j disjoint gaps. So the first gap, where the first interval is I0, I1, the I1, I2, and so on, and the last one is Ij minus 1, Ij, and we assume that all those elements are in a set I. Here we assume that J is a subset of I. I think that it's the best for, at the beginning at least, to think that J is just equal to I. And you may think that this is the set of integers, for instance. Okay, so if we have this these intervals, then what we do is something similar to R variational estimate. That is, we take the supremum over all interval and Ij, J plus 1. Okay, and we take the supremum over all possible differences. Well, equivalently, you may think that instead of this supremum, so what happens is that we look at the differences with the left endpoint of this interval, right? But equivalently, we may think that we have two parameters, let's say S and T, and we have differences between AT and AS, and both those variables are in this interval. And this is completely equivalent by integrality. Right, and so what happens next is we just take a small LR norm of those supreme. All right, so here we have okay. So another observation is that if for some reason, for instance, we would know that this supremum is okay. So first observation is that it's a bit inconvenient that this interval is open at the right endpoint, because what happens is that we can have functions which are non-constant and still the oscillation semi-norm is zero. Right, because these functions might be constants, well, local constants, right? So, for instance, if ij is a set of dyadic numbers, or well, even easier if they are integers, then what happens is that our function might be such that it is, for instance, 0 on the interval 0, 1, then it is equal to 1 on the interval 1, 2, and so on, and because we have right endpoints open, then this oscillation semi-norm will be 0. On the other hand, if for some reason we would know that this supremum is obtained at the right endpoint, then what we will get here is just square function if r is equal to 2, or let's say r function if r is different than 2. Right, so that's why somehow this oscillation semi-norm is much closer to the square function when r is equal to 2 than to variations. Okay, and from this definition, also it's clear that oscillation semi-norm is dominated by r variation semi-norm, because here we have a constraint which comes from the fact that we look only in these blocks which arise from our original sequence I. Okay, can you see that? Okay. So we have also some properties of this semi-norm, which are quite similar to our variation of semi-norm. So the first one is that if we have if we can write down our set J into two pieces, then it is dominated by the oscillation semi-norm computed on this first, let's say, interval or first set J1, and then the same for J2. And here, what is more convenient than in the case of R variations is that we do not care if those sets are disjoint, and we also do not care if they are ordered. And this simply follows from the fact that the supremum over such larger set is dominated by the sum of supremums over J1 and J2, and then we use a triangle inequality for small and large. Okay, so in this case, it's clear that this is. And the second observation is that the oscillation semi-norm is dominated by variations, and we already know that R variation semi-norm is just dominated by some constant times small power R norm of the sequence. All right. So do you have any questions? Okay, so we have more properties which are similar to R variations. So the first one is essentially the one which we have for the R variations, except that here I stated this this estimate for norms, so for functions, not only for sequences, but for for functions. So this says that the maximal operator, here we need to exclude the supremum of I, and this is connected with the fact that we have right open interval in the definition, but this is not important in applications. So here we have a supremum over LP norms of the sequence. So usually we'll be dealing with averaging operators, so they are contractions, and this will be just a constant. And here we have our oscillation summary. So what happens is that we have this sequence I. We compute oscillation semi-norm for this sequence I. Then we compute LP norm for the operator. We may think that AT is some averaging operator, which is on some abstract, which is defined on some abstract space X. And then what happens, we take the supremum over all possible choices of this sequence I, and also the supremum over the length of this sequence. Okay. So that's how the oscillation semi-norm looks in practice. Okay, so we choose the sequence, then we compute oscillation semi-norm, then we compute LP norm in this abstract space X, and then we take the supremum over all choices of this selection sequence I. All right, and what happens is that once we know that for any sequence I of length j plus 1, we can find a constant which depends on the length of this sequence, but not on this sequence itself. And if we know that this constant behaves well, so it suffices to know that if j tends to infinity, then this expression tends to 0. So in particular, today we know that in most of the cases, we will have a constant which in fact is does not depend on j. So the estimates are uniform, and then we will have this property, this assumption for free. Okay, but in the 80s, when Bourgain was originally proving L2 boundedness of pointwise convergence for the averages along squares, then the uniform bound was not available. So he in fact proved that for p equal to 2 and for r equal to 2, so two oscillations and estimate on L2, he was able to prove that this constant is small square root of j. Okay, and from this condition, it's sufficient because p is equal to r and it is equal to 1. So it's sufficient to know that this constant divided by the square root of j tends to 0. Okay, this is what I've mentioned last time. This is only a small improvement of the trivial estimate once we know that the maximal operator is L2 bounded. Because once we know that the maximal operator is L2 bounded, then we can bound this supremum just by maximal operator, and then we have j terms, right? And at the end we take the square root. So what we get trivially from the maximal estimate is the square root of j. So this is not sufficient to conclude that we have pointwise convergence, but we just need a small improvement of this estimate. Okay, so you need to work a bit. Here, not very pointwise convergence. All right, and I would like to give you a proof of this fact that is once we have this such constants which satisfy this identity, then we can conclude that the sequence AT converges almost everywhere on X. Right, so the proof will be a bit technical, but in some sense it's quite similar to the one which we had yesterday, which was that the space of functions. Well, once we know that the maximal operator is of weak type Pp, then the set of functions for which we have convergence is closed in LP. So this proof is somehow similar in the sense that we will proceed by contradiction as well, and we will look at the limit supremum of the sequence. So we assume that well, that's in fact the sequence AT does not converge almost everywhere on X. So first of all, we may think that our measure is finite by restricting to some subset of the original space X. And the fact that the sequence does not converge means that the sequence is not a Cauchy sequence. So in fact, it means that we can find delta such that the measure of the set for which the limit superior is larger than to delta is larger than to delta. Okay, so this is from the fact that this is not a Cauchy sequence. So then we can throw away this limit, and we can look at the sets A and itself. So it's clear that those sets are nested. So this sequence is decreasing, and thanks to the fact that we restricted to a set of finite measure, we can put the limit inside those sets. Okay, so far I did nothing. I just put this limit outside the measure. So then we can find n0 such that for all n's which are larger, this set which appears here is greater than that. Okay, but what I did here more is that I used triangle inequality, and thanks to that I can put s equal to n, and the price I need to pay is that instead of delta here, I have delta. Yeah.
So since the solution is now increasing more improvements for R equal 1?
Well, so far we didn't have oscillations here.
Okay.
But what we need to assume is this estimate. So for instance, if we knew that well, we will not need as much information if we knew that this works for R equal to 1. But what will happen in practice is that we will include R equal to 2, so then R greater than 2 are good as well. But if R is less than 2, then rather this estimate will not, at least uniformly in sequences. In the life of the sequence. So there will be no uniform bound with respect to J for these oscillations if R is smaller than 2. So somehow the endpoint for variations and for oscillations is the same. It's R equal to 2. But what will happen is that for R variations, the estimate for 2 will not happen, and for 2 oscillation it will happen. Okay. All right. So far we know that the measure of those sets for large enough n's are greater than that. Okay. So the only trick we did is that using triangle inequality, instead of writing this supremum, I get rid of one variable. Okay, so I just have to. Okay, so this is the last line from the previous slide. So now I would like to introduce, so I know how the supremum behaves, but in the definition of the oscillations, I have intervals. So what I want to do is I want to put the restriction in T from above. Okay, in order to get intervals. So we introduce those sets, and it's clear that if we let n to infinity, then we obtain the measure of those sets, right? And since those sets are increasing in n, it's clear that the limit of the measure of those sets is exactly the measure of that set, and we already know that this is larger than that. Right? So in that way, we can find large capital N such that if we restrict our attention to the supremum over interval n, then still the measure of those sets is greater than delta. Okay. And what happens here is that we can proceed inductively. So we can put as I0, we can put N0, then we hold some large M, so this might be our I1, and then we can think that our I1 is mu N, and then we can find another very large constant such that we will have a sequence of points such that the measure of the set that this supremum is greater than delta is greater than delta. Okay. Okay, so once we have it, we can estimate this expression which appears here. Okay, so if we change the order of summation and integration, then what happens is that we know that this expression here is greater than delta on the set which has measure at least equal to delta. So what we have is summation times of delta to the power p plus 1. Because we have delta, so delta to the power p times the measure of the set, which is delta plus 1. Okay, but on the other hand, okay, and this is a bit tricky. I didn't write this explicitly. So here, what we want to do is to get R variations, and we have P norm. So depending what is the relation between P and R, we want to use different things. So if P is smaller than R, we use not Cauchy-Schwarz but Elder inequality with our R over P, which is greater than 1. And then what we will get is this J to the power 1 minus P over R. But Q is the minimal element of P and R, so in this case it's P. On the other hand, if P is greater than R, we just use the fact that IP norms are nested. So just trust me that it can be easily checked that we have this estimate here. Right? And once we have it, then we can put J on the right hand side, so we can cancel out this one power. So on the left hand side, we have delta to the power p plus 1, and on the left hand side, we have some negative power of J times the oscillation element. So what we can do is we know that this oscillation semi-norm by the definition is bounded by this constant to the power p. Okay. So now we want to use our assumption. So we know that this limit is equal to 0. So when we use the fact that this power which appears here is exactly up to taking the fifth power there, is exactly this power of J, right? So if this limit is equal to 0, then fifth power of this limit is also equal to 0, and we exactly have this expression here. So on the left hand side we have some positive value, and on the right hand side we have 0. So we have a contradiction. Yeah, but the moral of this is that for R variations, it was very easy to observe that uniqueness of the R variations implies that the underlying sequence is a Cauchy sequence, and here we need to work a bit, but at the end, this gives exactly the same conclusion that if we have R oscillations, which are, well, in particular, if they are uniform in the length of the sequence I, then we have this condition, and we have pointwise convergence, obviously. All right, so this is the last semi-norm which I want to introduce. This one is, I would say, quite similar to R variations, as we will see later on. In some sense, jumps are some sort of endpoint for R variations. So what happens here is we consider a sequence of functions, and then we introduce lambda jump counting function. So what happens here is that we fix a number lambda, and we need to think how many jumps we have of height lambda. So this lambda counting function is the maximal value of j, such that we will be able to find points t0, t1, t2, and so on, up to tj. So we will have j intervals, and on each of them, we need to ensure that the difference of the endpoint and the endpoint is at least equal to 1. Okay. So what happens here is that we need to have consecutive points such that the difference of the sequence on each of them is at least equal to lambda. This definition is quite convenient if we want to make some stopping time arguments. However, in practice, it's hard to if you have a particular sequence A, then it's not so easy to compute this number j, because sometimes it's not optimal, and well, at first it's not clear what are the optimal choices of tips, because we need to have consecutive jumps. Okay, so sometimes it's better to take the point earlier to make more jumps later on. Okay, and this is a bit tricky, but in fact, what one can do is we can consider similar semi-norm, which I will call later on lambda jumps as well. So here the difference is that instead of having consecutive jumps, we allow that the jumps are not consecutive. So it suffices that we find j intervals such that on each interval we have a jump of height lambda. Okay, and from this definition, it's clear that this function is larger than the previous lambda jump counting function, because we do not assume that the jumps are consecutive. But on the other hand, playing a bit with the triangle inequality, one can show that this function is dominated by our original function once we take jumps of height lambda over 2. Okay, and my impression is that if we have particular sequence, it's much easier to compute this function. Okay. What is a bit annoying here is that we know that when looking at this lambda lambda jumps semi-norm as a function of f, this semi-norm has a quasi triangle inequality. So we have triangle inequality with some constants which a priori is greater than 1. And this is a bit inconvenient because, for instance, observe that, for instance, if we want to estimate some series, or if we want to compute the norm of the very long sum, then what happens is that each time we use it, then we increase this constant, right? Because if we apply it once, then let's say we have a constant k, but if we apply this twice, then we have k squared, then k to the power 3, and so on. Okay, so it grows with the number of terms in the sum. So what we would want to have is to know that there is an equivalent semi-norm which possesses the truly triangle inequality. And in this, this problem is somehow similar as the problem with the weak spaces for keys strictly larger than 1. I forgot to mention that yesterday, but in that situation, the norm which I gave you as a definition of the weak LP spaces, it possesses a quasi-triangle inequality, but if P is strictly larger than 1, then it's possible to define another norm which is equivalent and which have triangle inequality. And this is not the case of P equal to 1. And here we have similar situation, that is, if we assume that P is strictly larger than 1 and rho is larger than 1, then it's possible to introduce such semi-norm, which is equivalent to our original lambda jumps, in the sense that it is dominated by C times the original norm and from below and from above, and it has strength inequality. So in fact, if we do not care so much about the constant, we can think that this original semi-norm has strength. Right, and this is a result of Mirek-Stein and Zorin-Kranich from 2018, and they use K interpolation theory to construct this semi.
What happens with this law? Doesn't it make some genius?
Well, it's here, and let me think. But what kind of homogeneity you want to have?
I don't know. If you just multiply the sequence out. Okay.
Yeah, it's okay because you take supremum over lambda, and if you count this, then you count.
Yeah, that increases the
yeah.
percentage.
In fact, it's
I see, of course.
Yeah. Okay. Do you have any questions? All right. So okay. So what happens is that in fact this lambda jumps are smaller than the corresponding R variations. So if this R corresponds to that R, then lambda jumps are smaller. Well, I forgot to write the definition because it would be useful here. But what happens is that R variations are supremum over all possible differences in LR norm. And here we count the number of jumps. So if we fix lambda, then we can dominate, well, we can bound the R variations from below by lambda to the power R times the number of jumps, and then we need to take the root of order R. So what we get is lambda times the number of jumps. Okay, and it works at the level, it works pointwise. So we have pointwise estimate of these types, and then we can take LP norms and then supreme norms. Okay, so this tells us that the lambda jumps are smaller. But what is important here is the observation of Bourgain that essentially we can reverse this inequality as long as we assume that R is greater than rho. So for instance, if we have lambda jumps for the parameter 2, then it dominates all R variations if R is strictly larger than 2. Okay. In fact, I will give you a quite simple proof of this fact later on. But in practice, it's quite nice because if you want to prove R variations for R greater than 2, then it's obvious that we prove lambda jump estimate for rho equal to 2. Okay, and the difference between these two estimates, well, they are reversed, but the point is that instead of having LP norm, we have weak LP norms, and it's not possible to, in such generality, it's not possible to put LP norms there, and this is a very easy argument I will give you this argument as well. But it does not matter in the sense that if we know that for some operators, so instead of considering general sequence AT, we consider some operators, and once we know that we have lambda jump estimate for strong type, then we can estimate, of course, this expression by the strong LP norm, and then by the strong LP norm of the function f. So this would tell us that the R variations are of weak type PP, right? But by the interpolation, usually our interval will be open, so in fact we will have a strong type PP. Okay, so this does not have implications. Whatever you have here, it's okay. All right, so as I mentioned, it's not possible to put strong type PP here. And in fact, this is also true for R variations. So it is not true that this estimate holds for R variations if we put R variations on the left-hand side. So we put something, formally we put something smaller, so we hope that it would work, but still it does not work. So it's possible to find a sequence such that the left-hand side there, but with oscillations instead of R variations is infinite, and the left-hand side, which appears here, but with LP norm, is fine. Okay, and in a moment I will give you an example. Is very trivial in the sense that we just need 2 points and the time variable itself has 2 points as well. Okay, maybe do you have any questions? All right. So spoiling a bit, later on we will show that this kind of estimates are not true for R variations. So we can interpret from this estimate that somehow lambda jumps with parameter, let's say 2, are endpoint estimate for R variations if R is greater than 2, and we cannot, in the same sense, we cannot say the same for R variations. So for R oscillations. So R oscillations will not be endpoint estimates for R variations in this sense. All right. So this is the example which I've already told you about. So we want to have a function. So here I use a bit different notation. So instead of having the sequence AT, I just use the sequence F. So instead of A, I put F. And what happens is that R variations for all R greater or equal to 2 are infinite, and lambda jumps are fine. Okay, so the difference is that here I put strong LP norm, and there I have 3. All right, and the counterexample to this estimate with strong norm LP, and just an example to this statement is as follows. So what happens is we take the spatial space as Z, and time variable also is Z. Well, it's integers, positive numbers. So what happens is we fix a sequence which decreases. So this is a frequency AX. And on each coordinate, we put a function which looks like that at the first point it has value AX, and then it is 0. So it is almost a constant. Yes, so this is the definition. So the first variable is a spatial variable, and the second variable is a time variable. So we compute R variations or lambda jumps according to the second variable. So these functions are very simple in the sense that they have only one positive value at the first point, and then they are 0. Okay, so this is exactly this definition. So what happens is we have just one jump, because we have one jump from 1 to 2, and then the function is constant. So if we compute R variations or lambda jumps, we just need to look at what happens from point 1 to point 2. Okay? And for every x, we have different jumps, right? Because it's given by this sequence AX. But later on, it will turn out that this sequence which we have here is okay for our example. So first of all, if we compute the R variations, so if we look at the differences, there is only one trivial difference, and this is AX minus 0, so this is just AX, and it does not matter which power we take, because then we need to take the root of this function. Okay, so this is just that. So if we compute LP norm, well, if power of the LP norm, then we just sum all those things, right? And we can already observe that with our choice, this will be sequence 1 over K, so this is equal to infinity. Okay? Okay, do you see that? Well, I can draw a picture if you want of those functions. So then we want to compute lambda counting function. So what happens is that at each point we have just one jump. This jump is ax. So if we count the jumps of height at least equal to lambda, then we need to think if lambda is greater than ax or smaller. Okay, so since the jump is actually by ax, so if lambda is smaller, then we count this jump. And if lambda is larger, so the jump is smaller than lambda, then it is equal to 0. Okay, so once we have it, then we can easily see that if lambda is greater than the largest of all terms of this sequence, then we do not have any lambda jumps. Okay. On the other hand, if lambda is in between aj minus 1 and aj, then we count only lambda jumps on the variables which are smaller than j, because aj is greater. So for j coordinate, we have a jump of height at least lambda. The same happens for aj minus 1, aj minus 2, and so on up to a1. So in fact, if lambda is between those 2 points, then we can easily see that we have jump of length of height at least lambda for x's which are at most equal to j. And once we have it, then we can easily compute LP norm. This square root does not matter because this function is equal to 1 or 0. So it's clear that it does not matter. Well, this square root does not matter. And we can compute that if lambda is greater than 1, then it is 0. And if lambda is between those points, then we have j coordinates on which this function is equal to 1. So we have j here. Okay, and if we compute now the supremum, this is supremum over this function, which is quite easy to compute because this function is piecewise constant. So in fact, we have supremum over such a set because the optimal choice is that we choose lambda as large as possible. So we choose in this region, for instance, we choose lambda equal to aj. So we have aj to the power p times x jump, right? Okay, and for this choice which I announced before, this is just the supremum of a constant function. So in fact, we proved that this supremum the lambda jump semi-norm is finite because it is equal to 1 and our variations are. Okay. So this is a very simple example, such that this inequality here cannot happen for some time. All right, so okay, I have still something like 10 minutes, right? Okay. So this is the relation between lambda jumps and other variations, which I told you before. So this is an observation by Gauguin. So he was able to show that once we consider weak type spaces, then other variations for r greater than rho are dominated by lambda jumps. Yeah, okay. I think I will have time to give you a proof of this during the theorem. So we will frequently, at least twice on this page, use this simple estimate, which follows directly from the definition of weak spaces. So what suffices to do by homogeneity when we compute weak LP norm on the left-hand side, it suffices to take the corresponding, usually this parameter is lambda, here it should be probably different letter, but anyway, it suffices to take it equal to 1. Okay, so instead of having a supremum over some t to the power p times the measure of these levels are greater than t, is bounded by whatever, it suffices to consider one. Okay, so this is the homotopy argument. And A is just the right-hand side there. And here what we have is formally the fifth power of the left-hand side. So first we make a technical reduction that we want to assume that our sequence does not have jumps larger than one. Okay, so we consider this R variations for R equal to infinity, which is just some sort of maximal function of the differences. And we can easily conclude that if this function is greater than one, then we have the bound which we want to have. Okay, because what happens is that if V infinity is greater than one, it means that we have at least one jump of height one. And this is exactly what this inequality does. Right? Because this tells us what height and how many times. One jump of height. And now using this simple estimate, we can estimate this expression. Okay, so for free, instead of having this function, we can put this power, because on the right-hand side we have one. And now we can use this simple estimate, and what we get is, sorry, so this is here, and A is just a supreme over all choices of lambda, so this is lambda equal to 1. So we can easily conclude this theorem if we replace R variations by V infinity. So what happens is it suffices to estimate the rest of our set. So instead of considering just this condition, we can additionally assume that V infinity is at most 1, which is exactly equivalent by the definition of V infinity that we do not have jumps of height larger than 1. All right, so our aim is to prove that this set here has a measure which is at most a to the power p and x. Okay, so what happens then is we just use the definition of R variations. So this is the right-hand side, and we split those differences here depending on how large they are. So we do it diagonally. So this is why this j appears here, and we look at the jumps which are of height 2 to the power j, but here we split it into we can split into jumps of which are of height more or less to the power j. All right, and since we assume that we do not have jumps of height at most 1, then we can restrict to j's which are smaller than 0. And then having this estimate, we can easily estimate our set, the measure of our set x prime by the measure of this level set. So somehow we forget about this this additional condition here, because it is somehow written there. The summations of the j's which are smaller than 0. And what happens here is we once again use this simple estimate. And what we get is similar this way. Because if we look more closely here, then this function which appears here and is written in a very fancy way is just this function here. And the power of 2 is exactly the same, because here we have JR, and this term cancels out with this one because we have. Okay, and what we need to do is we need to consider 3 cases depending on if this power which appears here is greater than 1, equal to 1, or smaller than 1. Okay. And since I do not have so much time left, let us look only on the first case. So the first case is that rho is smaller. Okay, so this is what we've already done. So we have this estimate. And the first case is such that this power which appears here is greater than 1. So here we can use triangle inequality, because what I mentioned before is that weak spaces for p greater than 1, well, for the power which is greater than 1, have, well, essentially have triangle inequality. Awesome. So what we do is we just throw away summation j, because our power is greater than 1. And we get this estimate here. And by homogeneity, instead of writing well, p over rho, we can give this power here. So we end up with this space and price. Well, and we need to put this power here in order to have homogeneity. Right? Here we have 1 if we multiply. And once we have this identity here, then we are essentially done. You also observe that this term here is just one of the terms which appears there, right? With lambda equal to the power j. All right, so we can dominate this expression by a to the power rho, but at the end we will have a to the power p with this power there. And the rest is very easy because this series is summable because R is greater than rho. So here we have positive constant and place R center. Okay, this constant here is not important. All right, so I would like to meet the other cases. Maybe I will just mention what is used. So if the corresponding power is smaller than 1, and then we use some sort of triangle inequality, but which works once we consider a weak norm increased to the power q, and if q is strictly between 0 and 1. Okay, and we can conclude this theorem as well. Here is a very nice proof of this fact. Well, in fact, I recommend you to see that. I can give you the slides. And in the case when we are dealing with weak L1 norm, it's quite convenient to use Stein-Weiss inequality for weak norm. It looks a bit crazy, but what happens is that please think that just all functions Gj has L1 weak L1 norm equal to 1. So then if we would have, and let's say that we have a finite number of them. So if we would have triangle inequality, then we would, if we have, let's say, n terms, then we can estimate by n, right? But having this estimate, it means that here we would have n, here we have 1, so we have logarithm of n, and here we just sum from 1 to n once. So at the end, we get n log n. So what we lose is more than logarithm of the number of terms. Right. Okay, so once we introduce all those semi-nodes, we can come back to our ergodic setup and to our averages. And in fact, this theorem tells us that once we are in a linear and commuting situation, then everything is known. In the sense that we have our variational estimates, we have lambda jump estimates for for the parameter 2, our variations for our strictly larger than the 2, and oscillations for. So in some sense, it seems that both lambda jumps and oscillations can be seen as endpoint estimates for our variations. And moreover, these theorems are sharp in the sense that it's not possible to prove R variations for 2. It's not possible to prove lambda jumps for parameters smaller than 2, and the same for oscillations. All right, it follows from, in fact, it follows from Lepin inequality, which says, and we'll come back to that tomorrow, that if we consider martingale, so you may think that we consider dyadic cubes on RD, and instead of considering dyadic maximal function, we consider corresponding R variations R oscillations and lambda jumps, then similar result happens, and it is sharp. In the sense that we have R variations for R greater than 2 for these martingales. We have lambda jumps for 2 and oscillations for 2, and this is sharp. All right, and I think this is the last thing I would like to mention. So from this theorem, you might have an impression that, as I mentioned, two oscillations are endpoint estimates for R variations when R is greater than 2. But in fact, well, we still hope that they can be somehow thought as an endpoint estimate for R variations, but at least it's not true in the sense of Boolean. So earlier I told you that okay, it's not here, but if we consider LP norm on both sides, then we know that two lambda jumps with parameter 2, and they imply R variations with R greater than 2, but it is not possible to have similar thing with oscillations and R variations, as well as with oscillations and lambda jumps. In the sense that if we know that we have estimate for raw oscillations, then this estimate is not true, that we cannot conclude R variations. And this these counterexamples, because we claim that these estimates are not true, it seems that they are as strong as possible, in the sense that observe that on the right hand side we put LP norms, on the left hand side we put weak LP norms. So it seems that right hand side should be much larger than left hand side, right? But still, even if we put stronger norms on the right hand side, those estimates are not true. But still, we believe that, well, so in such a generality, because here we consider arbitrary functions f. This is not true, but we hope that once we consider, let's say, some operators, and if we assume something about operators, then maybe it's possible to somehow show some sort of estimates which will tell us that, let's say, two oscillations imply R variations for R greater than 2. Okay. All right, so thank you very much for today, and tomorrow we will.
Thank you very much, Szarek. Are there any questions? Jonathan?
I was just wondering if you could just join the dots a little bit with, so you have this oscillation estimate for these ergodic averages.
Yeah.
So how does that, so just, I mean, this is pretty obvious once you see the two things side by side, I guess, but going back to the numerology of what you need to get the point-wise convergence, could you just recap that?
Okay, why this estimate gives point-wise convergence?
Yeah, I guess it's obvious once you see the earlier slides.
Well,
I'm trying quite remember.
Yeah, okay. Some sort of, it is in the sense that here we have estimate which is uniform in J.
Yeah.
And if you are interested in point-wise convergence, what suffices to do is you take just the supremum over all sequences of fixed length. So you do not put this supremum over J.
Right.
And then it suffices to have a constant which depends on J and which has some admissible growth.
So this is a lot stronger.
Yeah.
Okay, I think that's maybe why I'm a bit confused. I was expecting it to somehow match.
Yeah, in fact, historically, Boolean was able to prove, once we derived this supremum, he was able to prove that the constant which appears here is of order small o of square root of 2 if p is equal to 2.
Right.
But here we have uniform.
Right, I see. Okay, Houston was too good.
All right, well, one would expect something like that, because observe that once we know that R variations dominates R oscillations, then for R greater than 2, we have this estimate, this uniform estimate from R variations.
Right.
So probably it's quite natural to think that we'll have oscillations with uniform velocity.
Now, ask another question that was a bit vague. So, are there any instances where one has maximal estimate, but one does not have any kind of, through any kind of oscillation?
Yes. Well, I think the answer is yes, and the situation. Well, I don't know if such situation happens in a continuous work, but in a discrete work, it happens for spherical objects. At least I'm not aware of any oscillation or variation or estimates for discrete averaging over series. But the maximal operator is.
So they fail or they're not known?
They are not known.
Okay, but they could still hold.
Yeah.
Yeah, I was gonna say that as far as I'm concerned, it's an open question, but it's not. It is not expected to fail, right?
Yeah, it's not expected to fail, but I think it's considered as a very. Okay, so we want to have an example for which you have maximal, but we know that there are no oscillations. Right? This is.
Yeah.
Okay, so from the answer is I don't know such an example.
Are there any other questions? If not, then thanks for both the lectures of today's talk. We meet now for a little announcement. So tomorrow evening we plan to go to a dinner to some place which is close by to the dormitory, like maybe 20 minutes walk from here. So I'm gonna ask tomorrow again if anybody is interested in coming just to make a booking. So I think if you want to join us tomorrow. Not I don't know. Maybe something between like 7 or 6. I will let you know tomorrow.
Where is pretty close from here. Yes, actually on the other one. Yes. I remember I walked. No, we don't. I'm listening to it. Yep. We don't always. I think it's cool. That's story. I think that's the one. That's the yes, I think so.